Yeah, sorry, I started recording late. Thank you for the heads up, Jessica.
No problem.
Just long story short, we have a couple of requirements for, for bonding. Those requirements are: we need orbitals that overlap from the two bonded atoms, one orbital from each atom. Once an orbital is used in a bond, it can't be used in another bond. In the region of orbital overlap from the two atoms, we need to share a pair of electrons, and that's going to give us a covalent bond. And remembering that those orbitals come from these wave functions, which are models for where those electrons exist around an atom, we're going to utilize these wave functions to help us model these three-dimensional molecules. But the wave functions for the pure atomic orbitals of hydrogen don't always help us as much as we'd like them to, because of their orientations in space and their shapes. And so in order to explain the shapes like the tetrahedral shape or the trigonal bipyramidal shapes and electron geometries that we see, we're gonna have to do something beyond just using those pure atomic wave functions that we get from the hydrogen atom. And so the way we do this, in order to explain the shapes we see, what we're going to do is we're going to combine atomic orbitals on the central atom. Okay, so we're going to talk about this from the standpoint of the central atom's orbitals to allow us to explain the shape of the molecule as a whole. And the orbitals of the central atom, remember when we talk about orbitals, those are wave functions. And so it's not just like adding two values. When you add functions together, you have to do linear combinations. And I'm not going to go through the math of all this. Suffice to say, there are certain things we need to know, and we'll distill it down to the things we need to know. And then that'll lead us to these new wave functions, where we take atomic orbitals and combine them, we'll get out these new orbitals on that central atom. Remember, we're just describing the orbitals on the central atom. And those new orbitals are things that we're going to call hybrid atomic orbitals, because what we're doing is we're combining the wave functions of, say, an s orbital and a p orbital. You put them together and you get new orbitals out that will help us to better explain the shapes of molecules that we see from VSEPR theory. And so rules for these combinations of atomic orbitals, okay? And this is a key one. For every atomic orbital that we put in, okay, we're going to get a new hybrid orbital out. So if we put in two orbitals, an s and a p orbital, we're going to get two orbitals out that are hybrid orbitals from the combination of those two wave functions. And the reason we're going to get these out is we have to take these wave functions into account, or we have to take the wave functions into account where we deal with the wave functions where they're in one phase versus another phase, and then the flip side of that, because it's somewhat arbitrary when we take into account, say, a p orbital where there's a positive phase, negative phase, versus negative positive phase, right? Or shaded, unshaded versus unshaded, shaded. So we have to take it into account both ways, okay? And so we're going to combine some of these atomic orbitals, but some atomic orbitals will actually remain unhybridized. So some of them will remain as pure atomic orbitals. And so we're going to look at this from two standpoints. One is sort of what I think is the most important picture for what we're using this for, is the shapes of these the hybrid atomic orbitals to help explain the shape of the structure. So we're going to look at the pictures. What happens to the pictures of those orbitals that we looked at, right? When we combine the wave functions of the s and the p orbitals, or the s and 2p of the p orbitals, or the s and 3 of the p orbitals, or the s and 3 p orbitals and a d orbital, et cetera, et cetera. So the shapes that we get out of that are going to be what help us explain the shapes of the electron geometries, or the shapes of the molecules. Now, as we're looking at the bonding, though, there are going to be two types of bonds that we're going to see. Okay, so when we think about bonds, remember we have to have orbitals that overlap, and we have to share a pair of electrons in the region where those orbitals overlap. And so orbitals can overlap really in one of two ways. They can overlap along the axis that is defined by the nuclei of the two atoms. So if you take one nucleus and the other nucleus and you draw a line between them, that's what we're going to call the bonding axis, okay? And so that bonding axis, if you have overlap of orbitals on that bonding axis, that's going to be what's lead to a bond that's called a sigma bond, okay? And so the overlap has symmetry along that bonding axis, okay? And that's the key to a sigma bond. When we look at other types of orbitals, it's more of when we see it in particular, what we're going to deal with is overlap of p orbitals that aren't pointing at each other, if you will, okay? So when we look at orbitals like p orbitals, say the px orbital from one atom and the px orbital from another, assuming that bonding axis is the z-axis, when you have that, you have sort of side-to-side overlap. And so when you think about p orbitals, right, so we'll draw these down here, right? If you think about p orbitals, right, if you have a nucleus in the middle here, right, orbital there is one phase, and the lobe on the bottom is the other phase. If you have a second atom that has its orbital that's overlapped with that first one, so basically here's your second atom, as these two atoms come closer together, the orbitals can overlap. And in this case, they're not going to be overlapping on the bonding axis. Okay, what they'll wind up doing is as they come closer together, the overlap will be above and below the bonding axis, okay? And so that's going to lead to what we're going to call a pi bond, okay? So a pi bond is the other type. So we have orbitals that overlap on the bonding axis. So an example of an orbital of orbitals that might overlap on the bonding axis, and we'll see these, or if you have, say, a hydrogen, an H2 molecule, where you have, there's one hydrogen atom, here's another hydrogen atom, so those are, say, s orbitals. Here's our bonding axis. As those two orbitals come together, right, you can get orbitals that overlap along where the orbital overlap is along that bonding axis, and your shared pair of electrons would be right in the middle here, right, as they come together. And we'll see that, so that we've seen that a little bit as a bonding motif for the localized electron model, but when we've dealt with the localized electron model, we've just assumed that we had these essentially sigma bonds where the symmetry is entirely along the bonding axis. But now we're going to explain bonding in a slightly different way, where we look at other orbitals or other ways of combining those orbitals to form bonds. And so the first way we're going to look at is what's called sp hybridization. Essentially what we're doing with sp hybridization is we're saying, well, we're going to take an s orbital and we're going to take a p orbital, and we're going to put those two orbitals together. And the first way that we're going to put them together is where we have the s orbital is in one phase. Okay? We're just going to keep the s orbital in the same phase, and we're going to look at the p orbitals as having, right, we know those lobes of the p orbital are in opposite phases. So if you think about the nucleus in the middle here, right, we're saying that the one phase, so if we see the plus and minus here, remember, we're talking shaded, unshaded. This is just the phase of the wave function. And so what happens here is if you have the wave function of the lobe on the right, right, is in the same phase as the wave function of the s orbital, right, then you're going to get constructive interference in here, right? And constructive interference leads to essentially a larger area of the wave function. And on the other side, where the wave function of the p orbital and the wave function of the s orbital are out of phase with each other, right? They're opposite phases. You're going to get destructive interference there, making that side, that overlap region, ultimately smaller. And that's if you add those together in that way. So here on the left side, you get destructive interference. And on the right side, you get constructive interference. And so if you add those two wave functions together in that way, you wind up with a new wave function that is what's called an sp hybrid orbital wave function. Okay, and that's from just combining those wave functions. But when we combine functions, we have to combine them not just in the one way where the p orbital in this case is one phase on the right and one phase on a different phase on the left, we have to do it in the opposite way as well. And so if we say, okay, well, switch the phases of the p orbital and then combine these again, right, we'll get another hybrid orbital or another wave function for a different hybrid orbital that's essentially oriented in the opposite direction but has the same shape as the one that we looked at initially. And so if you look at the region here, right, that's destructive interference. And if you look at the region here, that's going to be constructive interference. Okay. And so what you wind up with is a second, if you will, sp hybrid orbital. Come on. Okay, so essentially, and I'll get to your question in 1 second. Essentially, if we put 2 orbitals in, we got 2 orbitals out. Okay, now this is going to allow us to explain the shape of certain types of molecules, and I'm going to get to those in just a second. Yes, Maya.
How do you know if it's destructive and how do you know if it's constructive? To me, it just looks, they're both shaded.
Yeah, so that's where, so when we talked about shading of orbitals, one thing that I don't do, and I'm limited in my images that I can use here, is what I tend to not do is use pluses and minuses to represent shaded and unshaded. So you can think about the plus side there as being shaded and the minus side being unshaded. And then on the s orbital here, the plus is shaded. So where they're the same, right, that's going to be constructive interference, right? Where they're different, right, that's going to be destructive interference. Okay.
Oh, so it's not where they overlap? Or...
It is in the region that they overlap, but you see the region.
Plus and plus. Okay.
Yeah, there you go.
Got it. Plus and plus is constructive, and then plus and minus is destructive.
That's right. That's okay. Right. So that's talking about the phase of the waves in that case. So your plus and let's say your plus is the same as shaded, the minus is the same as unshaded. All right. So what we're going to do is we're going to use this to explain the shapes of certain molecules. Now, something to note though is that there are these 2 other orbitals left over that are unhybridized, leftover orbitals. Right? And so those remain on that central atom as pure atomic orbitals. Okay. And so an example of a molecule that would have this type of a structure would be something like, say, beryllium dihydride. Okay. If you think about beryllium dihydride, you can think, okay, well, here's my beryllium atom. That's just my nucleus. Coming out of that nucleus, we have these 2, and I'll try to change my color here so it's easier to see. We have these 2 sp hybrid orbitals. Okay, the sp comes from the fact that it's an s orbital and a p orbital. Okay, so here, what I'm going to do is I'm going to shade one side. Okay, there's my beryllium atom. There's one of the sp hybrid orbitals. And what we're really interested in and what we'll depict more often than not is just the big lobe of that orbital, because the big lobe is going to be the part that overlaps with the orbitals of other atoms to form bonds. On the other side, though, we have a second sp hybrid orbital with a small lobe on the other side. And so you can look at each of these sp hybrid orbitals on the beryllium atom as being the ones that overlap to give you the bonds with the hydrogen atom. So here's the, actually, try that again. Come on, there we go. I'm actually going to change my color for the hydrogen to make it a little easier to see. So if I have a hydrogen atom here, I can get overlap where the hydrogen atom's orbital is just the 1s, right? When we tend to look at hybridization, we usually look at it from the standpoint of that central atom in most cases. And in the case of hydrogen, hydrogen always is going to have its electron in the 1s orbital. It's not going to hybridize because it's only got 1 electron. It's only going to form 1 bond. Remember, the hybridization, this combination of these wave functions, is just a way of modeling in a more meaningful way or a meaningful way in some cases, depending upon how you want to look at it, the bonding between atoms to give us the shapes of the molecules that and how they exist. So if we look at the bonding in this beryllium dihydride molecule, we've got the two hydrogens, which each have a 1s orbital. Okay, that 1s orbital will overlap, right, with the sp orbital from the beryllium in each of those cases. They're each forming a bond. In this region in the middle, right, is where you'll have electrons, one electron from each hydrogen, and one electron in each orbital from the beryllium to have a shared pair of electrons. And that's going to be what forms your beryllium dihydride molecule. And so if you depict the Lewis structure of this, right, the Lewis structure, come on. Now my computer's being slow again, so 1 second. There we go. So if with my beryllium dihydride molecule, the Lewis structure looks like this. And remember, beryllium is one of those molecules that is an exception to the octet rule. It only needs 4 electrons around it. But this right here is going to show you a steric number of 2. Okay, and a steric number of 2, if you see a steric number of 2, is going to have a hybridization that is sp hybridization. And that gives you this linear shape. In order to have a linear shape, you need to have 2 orbitals that are opposite each other in their orientation. Okay. This will also work for things like carbon dioxide. We'll look at a carbon dioxide molecule a little bit later once we start to think about pi bonds, okay? But these bonds in this molecule, in this beryllium hydride, if you look at this as being all on the same axis, that's our bonding axis there. The orbital overlap, right, for both of these bonds is on that, on the bonding axis. So essentially what we're making here is we're getting a sigma bond, okay, on the right, coming from the 1s of the, the hydrogen 1s. Bonded to the beryllium sp orbital, okay? And on the right, also all that orbital overlap is on that bonding axis. So we're going to have a sigma bond coming from the hydrogen 1s bonded to the beryllium sp orbital. Okay, and so these here are sort of describing the bonding involved in this molecule. You're now looking at it not just from a standpoint of, hey, there's a shared pair of electrons between these 2 atoms. Now you're looking at it from the standpoint of, hey, these orbitals overlap and a pair of electrons is shared in those orbitals in order to make this molecule, to make a molecule that has this orientation. And so now we're starting to use shapes and orientations of the orbitals to help us describe the bonding in the molecule. Yeah, Maya.
What does the dash mean in the?
That's just the bond. That's saying,
oh, okay.
This hydrogen 1s orbital is overlapping with the beryllium sp.
Oh.
So another thing to think about in this is orbital energies and how those orbital energies come together. And in particular, we're going to look at the valence orbitals. Okay, if we think about the orbital energies of the valence orbitals, we're going to look at the beryllium orbitals, valence orbital energies. And so this is that hierarchy of energies that we looked at for the hydrogen atom, right? The 1s, the 2s, the 2p, the 3s, the 3p, the 4s, the 3d, etc. We're going to just look at the valence orbitals here. So for beryllium, the valence orbitals are going to be the second shell, so the 2s and 2p orbitals. And if we look at the electron configuration of just the beryllium atom, okay, and we're going to call that the unhybridized. Actually, here, I'll try to make this a little clearer. Give me a second. Okay, so if we look at the unhybridized version of the beryllium atom, or pure atomic orbitals, right? We have electrons in the 2s orbitals, and we have 3 empty 2p orbitals. But that doesn't help us explain the bonding in the beryllium dihydride molecule, because in order to have a bond in that beryllium dihydride molecule, we need 1 electron in each of these 2 hybrid orbitals, right? We can't have just 2 electrons in the 2s. That's not going to be able to share those electrons. So we invoke this idea of hybridization. We take our wave functions and we combine them. And when we combine them, what we get is we get out new hybrid orbitals. And so if we combine those wave functions, we get these hybrid orbitals where we essentially took, let's see if I can get, so we essentially take the s orbital, right, and one of the p orbitals, right, similar to what we did up here. We took the s orbital and one of the p orbitals, and we combine them, okay? And when we combine them, we get hybrid orbitals out. So again, we have an energy diagram. Here I'm going to say the hybrid, sp hybrid beryllium atom. And so here, this is hybridized. And what happens with those orbitals is that the 2s orbital and the 2p orbital that combine will combine to give us 2 sp orbitals. And these leftover 2p orbitals will come over and they'll be of the same energy, right? So those 2p orbitals that remain are the unhybridized 2p orbitals. And what you have from the s orbital that combined with the p orbital is 2 new orbitals that are the same energy, right? The only way they differ is their orientation in space. And each of those orbitals will have 1 electron in them. And so those orbitals with the 1 electron in them are the ones that can be used, right? These ones here can be used for bonding because they have 1 electron to share. And so you can think about each of these being one of these sp hybrid orbitals, right, involved in that bond, okay? And so that's, so depicting the orbital energies here, I have it on sort of a vertical axis. Another way you can do this is you can take your orbitals of the pure atomic orbitals, and you can say, well, we can do this in a similar way to the box diagrams that we did in chapter 7, where we have a 1s and the 3, excuse me, that should be a 2s and the 3 2p orbitals. We're just looking at the valence orbitals. And so the 2s for a beryllium atom has 2 electrons in it. And so when those are pure atomic orbitals, right, they look like that. When they hybridize, right, they're going to give us these 2 sp2 orbitals. And we're going to have the remaining 2p orbitals that are unhybridized. And each of those sp2 orbitals looks like that. Now, this is a way that we're going to look at orbitals in the lab that we do on Thursday, which is the Vesper lab. We're going to see hybridization. In the Vesper lab, they do the same type of thing, only they use circles instead of the boxes. So you'll have a 2s and then the 3 2p orbitals, where again, if they're the same energy, they're connected. So these are just same ways of, or similar ways of depicting these, just using boxes versus circles. Okay, and so this is going to be for the VSEPR lab, right? I just wanted to point that out to you now, so you're not confused by it when we get to that part. Okay, they depict it using circles, we depict it using boxes. If those boxes or circles are connected, it says they're of the same energy. So in essence, these sp2 orbitals on the right, these ones right here are the same as those, right? Those are the same. here we're saying that our energy axis is this direction, and if the boxes are connected, they're the same energy, okay? And so that's the sp hybridization. And this is going to be something, remember, this is for steric number 2, okay? And steric number 2 is going to be what we have for sp hybridization. Anytime you see steric number 2, the hybridization is sp hybridization, or anytime you have steric number 2, you also know that you have a linear electron geometry. So these things are all related to each other. The electron geometry, if it's linear, or if it's steric number 2, it's a linear electron geometry. Hybridization is sp hybrid, okay, for that central atom. Some molecules, though, will combine. So if we think about what this looks like after those orbitals combine. So again, this is sp hybrid. We combine these s and p orbitals, right, to get out these sp hybrid orbitals. And something we're going to see, right, this is the 2 sp hybrid orbitals here, right? These are the 2 sp hybrid orbitals that come out of the combination of the 2p and the 2s. And if you put those together, remember the nucleus is really right here in the middle at the origin of that. If you put that together, you have a couple of p orbitals left over. We can say, well, this is one of them is the p x, right? And this will be the one phase. This one down here is the other phase of the px, right? And then the other orbital that's on the other axis is the py in one phase, and the py in the other phase, right? So the long story short, these 2 orbitals are the unhybridized p orbitals. That's what those would look like. And those are going to be important as we start to talk about pi bonding in a little bit, probably tomorrow.
Professor, do you think you can draw just a generic sp orbital? I'm just trying to visualize it on 2-dimensional. Or is that's true?
That's what this is right here, right? This right here, that's one of the sp hybrid orbitals that we depict, right? And this is the other one. So there are 2 sp hybrid orbitals here.
Got it.
Okay, and so if you would, if you want to think about that as being the beryllium atom there, right? This is, if you have your beryllium atom in the middle, there's one of your sp hybrid orbitals, right? Here's the other one. And then those are left over. And this is not the best drawing, but the depiction is probably good enough, right? Then you can have overlap of this orbital because each of these will have 1 electron in them. And those orbitals are available now to bonding where you have your nucleus of your atoms in the middle, right? But then you have these p orbitals here exist, right? They're just, in the case of the beryllium dihydride, they're just unoccupied at that point. It'll be more important to look at those p orbitals when we look at something like carbon dioxide. And so here's an example of a BeF2 molecule. Down at the bottom, you can see a BeH2. So the BeF2 molecule, the fluorines that are the surrounding atoms in that case, are going to have overlap with the 2p orbital. So we're really, again, remember, we're only invoking the hybridization when we are modeling that central atom. We're going to keep those surrounding atoms, p orbitals, in their unhybridized form, unless we have to take that into account for some other reason, which we'll talk about a little bit more later, okay? And so these are illustrations of a couple of these other molecules. Obviously, the bottom one is just a better rendition of what I put together on that initial slide, the BeH2 molecule. So it looks a lot better than what I drew. And so that's your initial introduction to, remember, sp hybridization. If you think about this, right, we're talking about steric number is 2. The electron geometry is linear, right? The hybridization of the central atom is going to be sp hybridized, okay? And again, remember, if you have orbital overlap that's on this bonding axis, right? Anytime you have the orbital overlap that's on that bonding axis, that's going to be a sigma bond. So for both of these situations, right, whether it's BeF2 or BeH2, right, we're still having orbital overlap on the bonding axis, and you take each bond individually, right? In each of those cases, you're going to have sigma bonds, okay? And so you should be able to identify sigma and pi bonds. Once we get to the pi bonds, you should definitely be able to identify sigma bonds now. The orbital overlap occurs on that bonding axis. And so what we'll pick up tomorrow, I'm going to let you sort of absorb what we just did here for the beryllium molecules. What we're going to pick up with tomorrow is sp2 hybridization. And so the quick introduction of that is now that we're going to take and look at the sp2 orbital hybridization as being the central atom has an s orbital and two p orbitals that are included in this combination to give us the sp2 hybrid orbitals on that central atom. And so if we combine one s orbital and two p orbitals, that is where, by the way, the sp2 comes from, right? One s and two p's. When we combine those three orbitals, we will get out three sp2 hybrid orbitals. And so that's what we're going to dive into tomorrow as we go through a lot more of the orbital hybridization. And then eventually, we're going to look at bonding in a different way, because this has some really huge benefits to it in terms of looking at structures and shapes, but it doesn't allow us to do some other things, in particular talk about the energies of atoms and of molecules as compared to their atoms, nor does it allow us to predict things like magnetic properties, which we'll dive into a little bit more tomorrow and on Thursday for the bonding and the properties that lead to things like, is this compound magnetic or not? We'll dive into that more later. So we're going to end there. And let's see. Yeah. So we're going to end there, and we'll talk about this stuff more tomorrow. Okay. And so I'm going to stop our recording